All right. Welcome to the afternoon session of ICFP. It's my great pleasure to introduce Andreas Rossberg, who's going to give the afternoon keynote. Andreas has done a remarkable variety of things across the spectrum of programming, both functional and not, including working on module systems, parametricity, working on the V8 engine, working and most recently on WebAssembly, where he's one of the initial co-designers and co-edits the specification of WebAssembly. And I'm really excited to hear about what he has to tell us today. Thank you, Andreas.
Yeah, thank you for the nice introduction. So if you couldn't already tell from the nondescript title and Nick's introduction, I'm going to talk about WebAssembly, what it is, what is happening there, and what this community has to do with it. And spoiler is quite a bit. You'll discover probably some familiar faces on the way. So what is it? Let's get over with that first. It's a virtual machine. That's the shortest answer. But unlike other virtual machines you probably have seen, one distinct feature of it, it's a low-level virtual machine. And some of my talk will be about what that actually means. As a consequence of that, it's also a language-independent virtual machine. It's platform-independent as well. It has all these nice properties of being portable, deterministic. It has sandboxing. And it's an open standard, right? So it's not proprietary at all. Everybody can participate. And yeah, so this is a kind of a talk about a language if you want. And in a language talk, you would usually expect to see some code. This is not a talk like that. This will be more like an overview talk. And it's an assembly language, right? So it's not really the thing you want to dive through in a presentation. So I'm going to flash one example of WebAssembly code at you, in case you have never seen it, so you get like an idea. I will not go through it in detail, but just point out a couple of things. So first of all, S expressions, great. And maybe I should say first what this is. I hope you believe me that this is basically a translation of this little C function that takes a range in an array of doubles and sums up the elements. And there are a couple of things you can perhaps see here is like there are all these instructions and it's a stack machine. So you have all these stack instructions where the operands are implicit. You have things like loop constructs, label binders. You have branches to that label. You have definitions of functions. So all the code is organized into functions. And which have parameters explicitly, and these are typed. The parameters are typed. That's important too. Everything is typed. And on top of it all, everything is wrapped up in a module. So all of WebAssembly comes in modules which have explicit imports and exports. So that's roughly it. What it is in a very first approximation. I should also say something that it is not, and that might surprise you. Because the name tells you otherwise, it's not actually a web technology. So this name is, from my perspective, sort of a historical accident, right? It came out of where we started, and it was essentially a way to sell to the management that this is something we should be working on. Because at the time, at Google and Mozilla and Microsoft and Apple, those were the four big companies that were involved in the initial design. Management cared about the web and nothing else, right? At least the management that was responsible for the people doing this. So this was a nice way to kind of frame it. But really, we were very careful to not design it in a way that is related to the web at all, right? Or that makes it in any way dependent on the web or any of its technologies. And if you actually look at the official spec, I think the word web occurs exactly once in that spec. So instead, we wanted to design something that's actually more universal and that can be used in all sorts of environments. And that is what indeed happens. So WebAssembly is now running in all sorts of ecosystems and platforms from the web, obviously, but down to embedded and over mobile and cloud computing and so on and so forth. And that's why I like to, or prefer not to actually use the name WebAssembly, also because it's very long, but also because I don't like the web in it, because it's so misleading. So I usually just say Wasm. And the fact that this is this universal kind of execution environment was one of the two main reasons for me to be involved in this project, which is why I cared about it. So here's my little secret. The reason I got into this is because I'm a PL guy. I like designing programming languages. I like implementing programming languages. I not so much like implementing code generators and backends and runtimes and all that stuff. So I thought, wouldn't it be great if, I help defining this very nice abstraction that I can just target and then let all the other people that are much smarter and more experienced with that stuff do the work underneath it, and I never have to think about it again. So that was kind of like my secret motivation for working on this. I mean, had I known how much of my lifetime this ultimately ends up using up, I probably would have been able to implement 10 backends in that time, but I hope there's some added value to the whole thing as well. And the second big reason, to explain the second big reason why I want to be involved and got involved in this, I have to go back a few years. Into the 90s, when I was an undergrad student and first encountered this book. Some of you may have seen it. Some of you might even recognize that this is the first edition. So that's how old I am. I think when I first encountered this was like shortly before the 97 version of standard ML came out, so around 96 or whatever. So this is the definition of standard ML. And at the time I saw it the first time, it blew my mind, right? This is like a formalized specification of an entire language. And at the time, the only thing I knew was all these like prose definitions, hand-wavy definitions of languages that like just hope that they're somehow saying something that's approximately what you think they are saying. And this just took a completely different approach, made everything precise, and I thought like, yeah, obviously this is what we should be doing, right? Why we are not doing this, why is not everybody doing this? And later on, the SML folks, especially around Bob Harper, took this further, and they actually even managed to mechanize the whole thing, which took some additional steps through type theory and so on, but ultimately they had something they could mechanize in 12 and prove its sound, have a machine-verified proof that the whole thing makes sense. And for me, that was like a very strong inspiration for everything I did after that. I really thought this is the direction we should be taking as a community. So with WebAssembly, when that started to happen, that was finally the opportunity for me to put this into practice and demonstrate that we could actually do this in the mainstream, right? So WebAssembly, I'm very proud to say, is actually fully formalized. And by fully, I mean actually even more so than the definition of standard ML. By fully, I mean from the very first byte in your source code to the very last bit of execution. There is like no room for ambiguity or guessing at all. And not just that, we also have multiple mechanisations. Those were not done by me, but by other people. In particular, Konrad Watt did the first one in Isabelle. And then Konrad and Philippa Gardner's Wasm CERT team did one in Cork. But that was very early on. And Konrad's Isabelle mechanization even was done before we officially released WebAssembly. So here's the formal semantics of WebAssembly as it looked in our PLDI paper, in the original paper. That's all of it. So on the left-hand side, you see the operational semantics, all of it, ignoring the details of numerics, but other than that, it's complete. And this is the complete type system validation, as it's called in our thing. So it's just like not even 2 pages, right? So this shows to me how elegant these methodologies are that our community has developed. But that is just a paper, you could say, an academic paper, right? But we try to take it further and actually put this into the official specification. So WebAssembly specification, the official standards document, is centered around this formalization. So it includes everything you just saw. But for accessibility reasons, that is not, people didn't want to have something like the SML definition, right? Where you have only inference rules and that's all there is, and it's completely opaque to everybody who has not studied PL. So there was, of course, understandably strong pressure to also have some plain English in there. So what it also contains is a prose specification that is hopefully equivalent, saying with a bit more hand waving the same thing as the rules. So this is how the official standards doc looks, and you see like there are these rules in here. I mean the rendering is a bit ugly here. I think this is the PDF version, but anyway. So this is typing, this is execution, and you see like the formal bits here nested in somewhere they're small, and the rest is all this prose trying to explain the same thing in pseudocode COBOL or something. Right, so that's what we ended up with. And the prose here is essentially like a manual text rendering of the formal rules, which I did by hand, right? And it blew up the whole thing from 2 pages you saw before to roughly 200 pages. Plus, for political reasons, the whole thing also I had to write the whole thing in Markdown and use the Sphinx tool to generate it, which is like something I would never recommend to anybody. So if you ever have to write a serious technical document, don't use Markdown. It's a terrible idea. It doesn't scale at all, especially if you need to put math in it. So here's a screenshot of what the source code for this spec looks like. You have lots of markup and lots of math markup that for the nested LaTeX, and it's just horrible. But we have to maintain this whole thing as well. So not just write it. So first of all, writing the prose, as you can imagine, is extremely laborious, right? So like nailing down the formal rules took me maybe a few days, a week or something like that, because it's actually pretty simple language in many ways. But producing the prose took months, right? Because it's just stupid manual typing in this super verbose format. But it's not just also that this was done once and now we're done with it, we're over with it. No, I mean, we keep working on this specification, we keep adding new features, and every time we have to go through the same process for every proposal, right? Because the requirements for WebAssembly, there's an elaborate process for WebAssembly extensions and proposals, and one of the requirements is one of the deliverables is that you extend the spec, including both formal and prose rules. And all this stuff also has to be code reviewed. So any change to the spec is going through code review. So this stuff is a nightmare to code review for one, because LaTeX essentially is a write-only language, right? So the LaTeX part in the spec is like very hard to read and make sense of if you do code review. And the prose, I mean, it's just so verbose and buried in markup stuff, and it also puts you to sleep because it's so redundant and repetitive. And on top of that, one of the things with Markdown is super diff unfriendly because it's all layout sensitive. So, and diffs are your bread and butter when you do code reviews, right? So here's like a little screenshot from a very simple example of a diff on the spec. So you can maybe read like 3 of these pages, but when you have to read 30, you fall asleep, right? And it's like, and this is actually even a rather good case. So there are various proposals, as I said, and there are 8 ones that have already completed and that make up Wasm 2.0, which we like launched last year. But there are also like 25 or more still active. So this is gonna be a reoccurring problem. And these proposals range in complexity from like a diff that is less than 1,000 lines to diffs that are 100,000 lines, right? So most of that is tests. 70% maybe, but there's still a substantial amount of this spec text involved there that you have to read through. And ultimately, I have no trust that this code is read carefully. It's just impossible. I mean, most of the code reviews I have to do, but still, it's just like, I don't know. because all this is like manual labor, right? And there's not just the spec, there's also the reference interpreter we have. So another deliverable for a proposal is you have to extend the reference interpreter, which is written in OCaml, with a new feature. And that is another rendering of the formal rules. So I originally wrote the reference interpreter to basically be an executable version of the reduction rules and the typing rules. So here's like a screenshot of what that looks like. So you have to write that as well. So that's what every proposal author has to deliver. And then we also have the mechanisations. They are not required as a deliverable for proposals yet. We are not quite there yet. Maybe in 20 years this is something we can require. But in the current reality, that's not something we could. But still, we want to keep these up to date in some form. So that also has to be done. So I already said that's the Isabel one and the Coq one. The Coq one, by the way, is also hooked up to Iris. And there are other folks who are interested in Acta and Lean or a Haskell version of that. So here's an example of the Coq rendering. So it's again like the same thing in another language, right? So there are all these deliverables that you have to produce, and worse, when you do mechanization, like you do that manually, you translate, I don't know, paper rules into Coq somehow, and then you have to believe that they actually model the right thing, right? And that's eyeball correspondence, right? You can just roughly say, okay, this looks reasonable, but you have no way of checking that in any more specific way. So we are language folks, right? So of course, the thought that should come to your mind when you see a list like that before is, we should have a language for that, right? There should be something here. And I mean, all these problems were kind of obvious that we would run into them when we started 7 years ago. But at the time, I had no idea how else to do it. We didn't have the tech. We didn't have the resources. We didn't know our exact requirements for all these things, right? So we just went with what we could do, and that's where we ended up. But now, it turns out all the stars have aligned. So half a year ago, we had a Dagstuhl on WebAssembly, first Dagstuhl, and some people came together and talked about this and realized, you know what, we could actually do it. So these are the people involved here. It was particularly Konrad and Philippa in the Wasm cert team, so they had the expertise for like mechanizing the WebAssembly specification and doing the soundness proofs and all that. And then there was Sukyung with her team. They had the expertise from a project called Safe JStar, which is a project that took the JavaScript spec, which is also written in these pseudo COBOL, super hand-wavy, verbose style, and actually run it, like analyze it, interpret it, and construct an interpreter from it that could run parts of the test suite. So that is also closely related to what we need here, although it's a bit kind of like the inverted problem, but still like the whole experience of transforming between prose and the formalism is what we needed. So we decided we should just try doing this. So that's the currently called Spec Tech project because we don't have a nice title really, and the idea is to create a DSL for writing the WebAssembly spec. And this is supposed to be the single source of truth now, and everything is generated from it. So it should be easy to write and read, and to code review, obviously, and transformable in all these previous formats, in particular, including like a nice LaTeX rendering. So it should contain enough like formatting that you could generate really pretty looking LaTeX from it, but also generating natural language for some definition of natural from it, right? Right, and so I'm sure some of you are now like scratching their head and thinking, wait a moment, something like that has been done before. There's this one project, for example, called Odd and Lamb. Why don't you use that? And well, there's no simple answer. We definitely looked at it, but ultimately we decided that this doesn't quite fit our use case, and there are various reasons for it. But roughly, first of all, it's trying to solve a much more general problem, and thus is much more complex. And at the same time, it cannot do everything that we need. Like, it doesn't understand some of our notation. It doesn't have any domain-specific knowledge that turns out we want to use in some places. And we cannot just hack on it when we need to add new, like, special things, right? And then there's the whole social thing of, like, what's this long-term perspective on that? We need something. I mean, this is an industrial technology. It's an industrial specification. And we need something we know is still available in 20 years. And if it's no longer maintained, at least we would have to be able to maintain it, which is not clear at all for a project like that. So ultimately, we decided to do our own thing and just define a very specialized DSL that is just for our use case. And that just makes it a much simpler problem to solve, because we can just hack in whatever we need and ignore and cut corners for things we don't care about. And we can just tweak it any way we want. And we can maintain it ourselves. That's important too. So here's like a couple of simple examples. This is how you would like define the Wasm AST in that language now. And from that you can generate some nice LaTeX. That's not too exciting yet. This would be some typing rules in the syntax we're using, and this is kind of one reason this looks a bit odd maybe is this is optimized for diffs, right? So you want like every premise on its own line and not layout sensitive stuff. But from this you can generate very pretty looking LaTeX rules, inference rules. Here is reduction semantics. So you can also generate nice mathematical definitions from that, but more importantly, you can also generate the prose. So this is what we can do now with that. Like you see the formal rules in here as before on this other page I showed you, but it also generates all this prose, these algorithmic steps for expressing the same thing. It's able to collate rules that are related and turn them into conditionals. It can do all the cross-references in the spec. So you don't have to write this by hand anymore. I mean, it's still rough now. I mean, we're still like in the middle of it, but it's already super impressive and good looking. Here is the cock it can generate right now. Probably can't read that in the back, but just to show you that it's there. There's also work on an actor backend. There's a lean backend. So I don't think there's an Isabelle backend yet. But there's also no OCaml backend yet, but you see where it's going. So the big picture is like we now have this one source of truth, and the tool chain is, well, we have this tool, it just passes and checks it and generates some intermediate representation, and from that we can generate the LaTeX, we can generate the prose, but of course we can also generate the cock, and probably other things, whatever we are interested in. But the interesting thing now is if we had proofs for the cock theory it generates, so basically if we finish porting the proofs of the cock mechanization that we already have to the output of this thing, and that probably requires some engineering, so we haven't done that yet. But once we're done with that and the proof run through, we actually have validation that the LaTeX that appears in the actual document makes sense, right? Because this no longer is just an eyeball correspondence, it comes from the same source. And there's just some machine transformation in between. You still, of course, have to trust all these transformations there, but it's much less likely that you do weird things, weird mistakes. More interestingly, even, to generate the prose, you go to another internal representation. So the IR is more like a declarative thing. And then there's the AR, which we call the algorithmic representation. And you transform that by some process that is reminiscent of animation. And you can write an interpreter for that. And when you have done that, you can run the Wasm test suite against that. And when that succeeds, and we are, I think, 98, 99% there, 100 now? Oh, great. Okay. We are 100 now. So with that, we actually also have some validation that the pros in the spec make sense, right? Because this AR is essentially an AST for the pros. So altogether, we hope this gives a much higher level of assurance into language spec, even into a formal language spec than anything before. Right. So that was my kind of first half of the talk. The other half, I want to talk about more of WebAssembly itself, and particularly what I mean by it being low level, right? So I said it's a low level language, but what does that mean? And there are various properties you could enumerate, but kind of the slogan I want to give you, what I mean by it is, that describes it best is, it's an abstraction of the hardware. It's not an abstraction of the language. And that is a key difference to other popular VMs. Like when you look at the JVM or .NET, they're essentially like a relatively thin abstraction of Java or C#, right? But we're coming from down here, not from up there. So that's very different. And the consequence of that is that all the languages that run on it are actually equal citizens. Like no language has any privilege there, right? They all just see something as virtual hardware. And as far as I'm concerned, this is really the only way to do a language neutral virtual machine. You have to be low level. Everything else will just lead you into whatever. So it's language neutral, but it's also platform neutral in the sense that you can embed it in any host environment you want. It's just like abstracts a little bit of your CPU, right? And there are actually by now, I think, almost a dozen different implementations of WebAssembly that you could pick and embed in your application, in your environment, whatever you want. But this is like a nice slogan, but what does it mean concretely? So more concretely, what is WebAssembly? Yeah, I kind of already said it, but it's like virtual instruction set architecture that is supposed to map more or less one-to-one to instruction sets of actual hardware. At least in the first approximation, and with WebAssembly 1.0 that we were pretty close to that. And an important characteristic as well is, and a consequence of that is that it has a very transparent and explicit cost model. So you always know what's going on when you have a WebAssembly instruction and you know what hardware you're running on, you probably know what instruction it's executing, or maybe a short sequence of instructions. There are no hidden costs, right? Like no hidden allocations or branches or anything. All that should ideally be totally explicit in the instruction set. And the slogan here is that always comes up is we want predictable performance, right? So you really want to know what's going on the machine level. Another part of it is there's no such thing as an object model at all. Right? So you have memory, but anything you need to build in terms of that is related to your language, you have to model yourself. And it's also assumed that the VM can be pretty simple because all more interesting optimizations have already been performed by the producer, so the compiler generating WebAssembly. The engine doesn't have to do anything clever or fancy at all when it runs your code. It still has to do JITting, right, because it has to translate the bytecode to whatever native code you're running on, but that JIT can be pretty straightforward and dumb, ideally. And it can even run ahead of time because you're not relying on any kind of like dynamic optimizations or recompilation techniques like they are popular in modern VMs. So this is the general idea, but to what extreme can you do that, right? How low can you go? And obviously, you have to make some compromises. So we're always operating in this like vicious triangle of conflicting goals with performance and simplicity and generality, or actually it's a tetrahedron of conflicting goals, because hovering above all of them is like safety, and with that portability as the one thing we can't compromise on, right? It has to be safe. So we have to do in ways that remain safe. And balancing these constraints sometimes just necessitates raising the abstraction boundary relative to what you have on real hardware, because real hardware doesn't care about safety. So sometimes we have to do it, but that is where often the confusion comes in, like even on the WebAssembly committee where people start arguing, what does that like imply? And you should not think of this as a free pass. Just because we have to raise the abstraction of something shouldn't imply that we can raise it to arbitrary height. You should always do the minimal thing, right? If you can decompose something into simpler things, you should do so. You should still stay faithful to that kind of overall, slogan. So, and we can observe this becoming more and more interesting question over the evolution of the language. So with WebAssembly 1.0, everything was pretty simple, really. This was intentionally designed to support low-level languages, right? So to get out of the door quick, those were like our first line of customers that were already on the web. So we wanted to accommodate them. And we intentionally thought of like more like high-level language support for later. So that essentially is just the instruction set, it's just the intersection of what you find on actual hardware. And it really only knows machine types, right? That's all you have. Even pointers are just integers in that version. And the memory itself, you really just have a flat array of raw bytes that you address linearly. So the one compromise you have to do, there are bounce checks when you access the memory because safety, right, obviously. But this usually can be implemented with just virtual memory techniques. And on top of that, you have a couple more notions like functions and tables and globals, and then modules which bundle the whole thing together. So this is where it already gets somewhat more interesting. So let me take functions as an example. So if you look at machine code, there's no such thing as a function, right? You just have code in your memory. You can jump to it. You can pass something in registers or the stack. That's not the case here. Our code is organized into functions, and they're like a primitive notion. So you define a function, you define its parameter types and arguments, and you have explicit instructions for calling them and returning from them. And the reason for that, there are multiple reasons, but the obvious ones are like, we don't want to expose the stack, right? So in WebAssembly, there's no way to get a handle on the stack at all. It's completely encapsulated, and that does away with a whole range of attack vectors that you have with native code. But there's also a performance reason, which is that when you generate WebAssembly code, you can't know what architecture you're running on. It might be like register-deprived architectures like x86, original ones, or ones that have tons of registers. So how can you optimize for that on the producer side, right? So this is something we have to leave to the engine, where we have to raise the abstraction a little bit. Similarly, we also have function tables. You can't get a function pointer directly, and again, safety reasons, we don't want to expose physical code addresses, right? And what that actually implies is that we don't actually have a von Neumann architecture, we have a Harvard architecture. So code is completely separate from data. But still, that's the abstraction level we stick to. We could go higher, right? We could turn functions into closures, we could have methods or anything like that. Could go crazy with it, but we don't. It's just code. It's just code pointers, and we stop at that. WebAssembly 2.0 last year added a couple of more things. They're still fairly low level, so multiple return values, not too interesting. The big thing it added was vector instructions, but again, super low level, just exposing what hardware actually has. So there's one new type, which is the 128-bit vector. There's one thing that is a bit more high level where we start going into the direction of supporting more high level stuff, which is we now have new types of opaque references. So you can now actually pass around in first class manner a pointer to a function, but it's completely opaque. You can't see its bit pattern, which also means you can't store it in memory and things like that. So that's a bit higher level of abstraction if you want. And then there are instructions like memcopy and friends, which we added again more for performance because every architecture has its particular tricks how you can make that fast. You could do it in user space, obviously, but then you wouldn't be as fast as you can do when you know your architecture. But now what we have been working on the whole time is WebAssembly 3.0. There's some chance that we are actually being able to ship that, or at least create like a release candidate this year still. And that has much more interesting new features. So I'm going to walk through some of them because they might be interesting to this audience in particular. First of all, we get tail calls. Finally, we get tail calls. Thank you. Yeah, this was a long ride. I think I wrote the proposal 7 years ago, but it just took ages for engines to implement it. And that is very simple. It just adds 2 new instructions, which are explicitly tail calls, right? So the idea here is, again, be explicit. There's no implicit optimization, tail call optimization in the VM. The producer has to do that optimization and generate the right instructions if it cares. There are also exceptions. I might skip over that a bit faster. They kind of look like ML exceptions if you want, except that the catch clause just it has a jump label. So if you catch an exception, you just jump somewhere. It's not like a whole structured thing. But other than that, it's relatively high level, maybe more high level than you would expect from assembly language. And again, the reasons are things like typing safety and also composition across module boundaries and so on. On the other hand, it's not, it's not super high level because of the labels, right? Sorry. And the other, probably the biggest new feature and the most controversial one by far is we're now adding built-in support for garbage collection. So the first thing you should probably be thinking at that point is why? Can't I do that myself? I have this whole machinery at my hands, and yes, you can. And people have done it, and people will continue doing it, and it's not a bad idea. Depending on your requirements, you may have to do it even in the future, but it comes at a cost. And the cost is the abstraction level that WebAssembly operates on. So when you implement a garbage collector on top of WebAssembly in user space, you run into some of these restrictions, right? You don't have access to the stack, you don't know what the registers are. So you have to maintain a shadow stack, things like that. All of this will come at a cost. Essentially, GC is kind of like the worst case scenario for working on top of an abstraction like WebAssembly, right? You also pay for the bounce checks all the time, although you kind of already know this can't fail, but the VM can't know only because the user code knows. So that's one big reason why we want to build it in. And then there are others, like, for example, exchanging reference with the host environment. So this is something that, for example, on the web is relevant, where people want to be able to pass reference to DOM objects through their WebAssembly code. So that has to be safe. And then there is the problem of when you have multiple runtimes that might run in the same WebAssembly process from multiple languages, they have competing heaps, and you have all these problems. So performance problems with competing heaps and competing GCs, which you want to avoid. So we want garbage collection, but still we want to kind of stay true to our motto of being low level, right? So what does that mean? We really want to strip it down to the bare basics. And that means no complex types. It's just tuples and arrays. That's all there is to it. And they really just describe memory layouts. They tell the GC how to lay out your data structures, and that's it, right? They don't tell the GC what they mean. And if you're compiling a high-level language, whatever Rube Goldberg machine of type system that implements, you have to lower it to this very simple WebAssembly representation types. Basically in the same way that you have to do with a native compiler. One additional thing we also provide is, as a primitive, is tagged pointers in the form of unboxed scalars, which are also a form of reference that's compatible with these other references. So this is a unique feature compared to other VMs, and also, again, part of the story of enabling like language runtimes to do all these low-level things on top of WebAssembly. Very quickly, what this boils down to, if you have seen WebAssembly code, you get these new 2 forms of type definitions, and you can form a reference to these. And on top of that, you have this primitive I31 reference, which is the unboxed tagged integer. and you have kind of the canonical instructions to deal with them, right? So operationally, there isn't really anything interesting going on here. It's really just the obvious stuff. I mean, there are a couple more I'm not showing you here, but it's kind of what you should expect. Like if you know, for example, OCaml's Lambda language, then it looks similar, except that this is typed, right? So, and that is one of the challenges too. It's typed, so we want to avoid any kind of runtime checks when you access something, right? So all the types of reference, they're really deeply typed. So you reference something and the struct for every field, it also declares the type. But obviously, we can never be expressive enough to subsume all the source level type systems out there. So we need to have an escape hatch, and that is casts. There's some form of casts built in here where you can work around the WebAssembly type system. I built a whole case study of a complete ML compiler. I'll skip over that. I also built a object-oriented compiler with that to validate the design, but anyway. So this was long in the making. It's now already implemented, I think, in the major browsers, at least Chrome and SpiderMonkey and Edge. And there are already various compilers in different stages of development that target it. And the OCaml backends that are also in the works are also going to target this. It's a bit more difficult for some other languages like Go or Haskell because they do more tricky things in their garbage collectors, among other things. So they might not be able to use that right now, or maybe ever. It's not clear, but there's definitely a lot of room for improvement in the future. This is kind of like the first cut of our support. So that's WebAssembly 3.0. There are a couple more things I didn't mention here, like larger memory space and threading. This is coming now. But for the rest of the talk, I want to present two things that we are also working on that are, again, more interesting in terms of, advanced language features. So we are not done yet. There's still a lot to come. And one is the topic of continuations. So there's a big gap in WebAssembly right now. It doesn't have any means of expressing control abstractions. The stack is not exposed. You can't build it yourself. You're basically screwed. So if you need to generate any of these, you really have to jump through hoops, and you can't do it within WebAssembly itself. And of course, this is a long known, we know this, we have known this from the beginning. It was just, it took its time to become high enough priority with all the other things to work on it. And when you talk to people on the WebAssembly committee or compiler folks, what they usually will say is, what we need here is, we need a way to do stack switching. Because all these abstractions basically mean you have multiple stacks and you can switch between them. To translate that to this audience, what they mean when they say is, we want continuations, obviously. That's kind of a more structured way of thinking about it. And I think I'm also preaching to the choir here when I say that, when people say that, what they really mean is we want delimited continuations. Right? Oh, sorry, that was going too fast. Screwed my joke. Yeah, so, and since effect handlers turned out over the last 10 years to be a particularly nice way to provide delimited continuations, that is what you really mean, or should mean. or this nodding like vehemently, of course. So that's a project we're working on now, or have been working on for, what is it, 2 years, more, 3 years already? With a bunch of folks, some faces you might also recognize, who are kind of experts in this field, right? So we want to add effect handlers in some form to WebAssembly. But there are, again, challenges, and they have to do with this being a low-level language. So one is, it has to work without garbage collection, right? So even if we have the GC proposal, that should always be an optional thing and not a dependency to use to compile these control abstractions. Also, we don't have closures. Like, almost all the literature on effect handlers and continuations kind of assumes that closures are a total natural thing that you can just use. No, you don't have them here, right? Like, you need to have a mechanism that somehow allows you to work around it. You also, I mean, you have recursion. With tail calls, you now even have tail recursion, but you don't want to rely on it. I mean, this is more like an imperative language. You have loop constructs, so you want to be able to use that with loop constructs. With the imperative control structure, that is the more natural choice on that level. And as I said earlier, you want a transparent cost model. So you don't want like stacks being allocated without you knowing when that is happening. It has to be very explicit. So these are a lot of constraints that are kind of fly in the face of what continuations and effect handlers usually look like. But I'm just gonna very quickly show you the design we have. So we basically built on top of the exception handling proposal that's already there. So we kind of generalized this notion of tags that we have, which shouldn't surprise you. So they can now have results. And we have one suspend instruction, which is essentially your perform. And the dual is resume, that takes a continuation and its arguments and essentially applies it. And then we have an explicit instruction to create a continuation from a function, right? So this takes a function reference and creates a fresh continuation, which when you invoke it will call that function and maybe ultimately return. And the one thing missing here is, well, what happens when that actually invokes a perfect? So where does the suspend go? Where are the handlers? And the handlers, oh yeah, sorry. One big advantage here is that continuations now are basically a representation of stacks. They are kind of like a proxy to a stack out. And handlers are tied into the resume instruction. So every resume instruction has a table of effects and labels it would jump to when an effect occurs. And that label then gets the arguments of that effect plus a new continuation for resuming that same stack. And that's all there is. I could say much more of it. It's a very interesting topic, but I think I have to hurry up a bit. And also we have a paper on that at Uppsala. If you're interested, you can read it. And this is an official proposal. And we have a prototype implementation of it as well in Wasm time, which is one of the major non-web engines. And the last kind of thing I want to talk about is components for WebAssembly. So WebAssembly modules, I mentioned them in passing a couple of times. WebAssembly as a module system. Every binary comes as a module. And the module is fully encapsulated. So except for anything you explicitly import and export, the content of a module cannot be accessed. So it's a proper module system. And since it has imports, essentially a WebAssembly module is first order ML functor, right? And interestingly, it's a closed functor. There are no ambient capabilities in WebAssembly. You can't do anything except if it's given to you as an import. And that is the essential property to have sandboxing, right? So everything is a closed functor. But it's a first order functor, so you can just pass in values. But linking these things happens completely outside the language, right? The language has no means of expressing that. This is expressed in terms of the API of the embedding language, like in JavaScript, you have an API to instantiate modules, or in the C API. Oh God, what's going on here? Sorry. Sometimes it double reacts. And so there's no way to express linking. And also you cannot bundle modules in any way, right? They're just these isolated things, and all the glue basically has to be somewhere else. There's no standard way of expressing it. So, but there would be many use cases for having a standard way of doing these things. And in particular, Luke, who's like one of the fathers of WebAssembly, is working at Fastly now. So Fastly is this company that is betting heavily on WebAssembly. They're, I think, the largest content delivery networks, and everything they do is in WebAssembly, right? All the content code they deploy is WebAssembly code, and they really are in high need of like having more advanced methods of deploying code in interesting ways, doing virtualization and stuff. So he came up with this whole idea of a component model and a linking language he wanted. But that is a complicated problem, so we got together and tried to solve it in a PL-ish way. And he was interested in applying the right solutions. So what is the thing that we want to build there? It's kind of, we want to reintroduce the notion of software components. And I know this is a kind of burned kind of thing. It has been tried many times in the past and more often than not failed in a way. But maybe this time with the right foundation, we have a chance of getting it right. So another way of looking at it is we want to define a language layer on top of WebAssembly with which you can describe modular structure. So you can specify the bundling of modules, you can actually import entire modules, and you can describe how they should be linked together, what the life cycles are of instances and all these things you need to be able to talk about. And Luke kind of designed all these things and came up with stuff, and we talked, and at some point I realized, you know what? You've just reinvented the higher order ML module system. And when we kind of polished it and worked it out in detail, that is essentially what it ended up being. It's a form of the higher order ML modules, right? It looks a bit more low level because WebAssembly, but the essence of it is that. So a component is really just a higher order functor, and an instance is a structure, and linking is functor application. Not surprising to ML people, but now we can put it in the mainstream. We can sneak it into the mainstream. And there's also a notion of interface types, which I won't really talk about, but which allow you to describe signatures in a way that is not language specific. And then there are ways of, it includes ways of, for languages implementing these components to lower and lift their specific representations to this language agnostic interface language. And of course, it comes with the formal semantics. Okay, so this is also a proposal at stage 1, I think, component model, and Fastly is putting a lot of resources into building this for real with all tooling and around it, and they really want to release it this year, the first version of it. And also, this is kind of the groundworks for making WASI more practical. So WASI is one big effort called WebAssembly System Interface. It's kind of like a generic framework for defining portable WebAssembly modules that model OS abstractions or something, or can virtualize them, so pluggable in various ways. And it's basically the thing you want to use if you run WebAssembly outside the web. Okay, I think that's all I had. So the takeaway from this talk, first of all, it's spelled Wasm, not Wasm. Hopefully you've seen that. It's not an acronym, no reason to shout. It's not a web technology. It's a low-level and language-neutral VM. And it's fully specified formally. And I hope I convinced you that WebAssembly is a technology that is worth considering for you, both as a compilation target if you're like a language implementer, right? Because it's running basically everywhere nowadays. But it's also an interesting subject for all sorts of research questions. And I could probably give half a dozen more talks about specific things I really only like hinted at in this talk. All the interesting questions we have to solve. And yeah, the ICFP community is already heavily involved in various ways here, right? So this was one thing I wanted to bring across. And that is because this is actually, the whole WebAssembly process, standards process, is an open process, right? It's an open standard. The committee just meets online. Everybody can participate. It's bi-weekly meetings. There are no prerequisites to showing up there. If you're interested, you can just, well, maybe not this link's, well, maybe the first link might even tell you how to do that. But it's like, if this is something that would interest you, I encourage you to get involved. We need more smart people, more people with proper language background to turn this into continue this being the right thing, doing the right thing. That's my talk. Thank you.
Thank you, Andreas, for a very inspiring talk. It's great to see this confluence of amazing PL ideas working well in an industrial standard. We have plenty of time for questions.
Great, thanks Andreas. So I'm curious about why, given the cast of characters involved in WebAssembly from the beginning, yourself included, and the well-understoodness of the tail calls and why they're important, how did it take so long to get tail calls in? What were the tricky problems that meant it was long delayed?
I'm not sure I understood the first part of your question. It was pretty much of an echo here, but like...
I was just saying, given the cast of characters that was involved, it's not as if a bunch of ignorant people designed it and then you retrofitted tail calls, right? You were there, and a lot of other very clever people were there. So there must have been something tricky about it.
So I didn't show you the kind of process that we have for proposals, but one of the requirements for something to get standardized is it being implemented successfully in 2 production engines. And that's usually the barrier where something cringes to a halt. And that has happened with tail calls in particular. And because engine vendors essentially never prioritized it high enough, there's so much proposals going on, they have so much work to do that they never really considered tail calls as the most important thing right now. And was also something with Microsoft, but we can talk over it here.
Adam?
So I understand the core part of the motivation of WebAssembly being that it's relatively straightforward to compile to the native instruction sets of popular architectures to get good performance. But does the WebAssembly community worry that it'll be increasingly impossible to write assembly programs with good performance, even if you write them directly in native machine languages, if you're not taking advantage of parallelism through accelerators or other kinds of computing substrates that don't use an input format that looks like assembly language? Is this project going to get left behind by any use case that really want the maximum performance going forward?
Yeah, that's a good question. So actually this has... So he was asking about, essentially, what about GPUs or other like platforms, computational processors that are not what this is modeled for, right? And which are pretty important nowadays for certain applications because they use them as co-processors to solve certain problems. And this is a question that has come up, and some people ask like, okay, can we target, I don't know, a GPU with that? And obviously the design doesn't fit that at all, right? So I don't have a good answer for that. That is not currently something that is our like target use case. Yeah, I don't know. I don't have a good answer, but it's a very fair question. But it's also not something usually, probably the use case where you care for portability that much.
Alan?
All right. So comparing Wasm to LLVM, which is like another player in this space, one of the big differences seems to be that LLVM has a model for undefined behavior, and that's not a feature of Wasm. So I was wondering if you could say something about that design decision. So the comparison with LLVM, like that was one of the big questions we often got in the beginning, like why don't you just use LLVM? And I should say, well, some of the genesis of WebAssembly is it grew out of ASM.js on one side and the whole Pinnacle effort at Google on the other side. And Pinnacle was using LLVM bitcode as their standard format, right? Because they were hoping that they could like reuse a lot of the technology. Turned out it didn't work at all, really. LLVM is a terrible format for VM. It's not, despite the name, it's not actually designed for that at all. It also turned out it was completely underspecified. The backends were much too slow for VM, and it also was a moving target. And then the whole like undefined behavior thing was yet another thing. So in the end, they basically ended up redoing most of the work that LLVM could have like done for them, and they didn't reap much benefit out of that. But the biggest thing for us really, we wanted a well-defined semantics that has no undefined behavior whatsoever, and that's naturally not something you will ever get of LLVM, even if you tried hard, I think, even if you try to constrain. It's just not designed for that. I don't know if that answers your question now.
Neil?
So in your talk, you said you're Wasm already has exceptions and you're adding effect handlers to it. You know, what's the story for their interaction? Does that get complicated?
No, it's kind of similar as an OCaml, right? They're very closely related. So, I mean, you could always view exceptions as a special case of effect handlers, but in reality you don't want to because the cost model is quite different. So with an effect, you need a new stack essentially, right? With an exception handler, you don't want a new stack. That would be a cost you don't want to pay. So the very first design actually we had for effect handlers was really as an extension of the exception handling proposal. But then we ended up having annotations on every exception construct to say, is it like, can it resume or can it not resume, right? So basically we already had two different sets of constructs, and that was necessary to reflect the performance, the different performance behavior. But other than that, so if you have an effect declaration attack, you can actually use it for both. They're the same thing in a way, but and you can throw exceptions out of a continuation, and it would, since they are structured continuations, right? They do the clean thing. There shouldn't be any surprises. All that we have modeled, and yeah, it should be doing what you expect it's doing.
Okay, thanks.
I had a question. The spec tech part of your talk was also really interesting. What's the story for migrating the large amount of documents you have now to this new thing?
Yeah, good question. Well, hopefully a large amount of what's in there you don't have to port because it will get generated, right? So my vision of what we will end up with is we will have stubs of all the chapters of the spec, and there are like splicing commands in there which you then run the generator over, and it fills in all the pros or the rules in that thing. And so you really just have to keep the skeleton of things. I mean, obviously there are parts like introductions or meta-level explanations that you still have to write manually, but kind of the bulk of it, I'm hoping you don't have to do much work.
Do you worry that language implementers have used the current spec to base their implementations on, and moving to this new thing may introduce subtle discrepancies?
No, I mean we have, so the semantics is not supposed to change at all, right? It can't, that's like a total no-go. And we also try to keep, basically that's one reason why we built our own tool, so we can build it such that it essentially uses the exact same formulation we already have in the spec, and we don't have to do major changes to that, to the structure of how the language is specified when we move over. It's just a way to generate it in a less laborious way.
Yeah, I really enjoyed that part. Here?
So I had a question about, I was a bit surprised when you said, oh, we've got all of these different reference semantics, implementations in different languages, and you said, well, let's create another language as a solution to this. I would have thought so I was just interested about your thoughts there of, is it better perhaps to have multiple implementations in some way to see whether or not they're consistent as a means of trusting versus having the single source of truth?
Yeah, I mean, I could see that being an advantage. In practice, though, since WebAssembly is still semantically in many ways fairly simple, I don't remember us ever having discovered like serious discrepancies between the different implementations. And we have a pretty exhaustive test suite as well. So even between different engines, and I view that as actually part of the success story of this whole formalization effort, there has never been a discrepancy between different WebAssembly implementations in the wild, except for straight out bugs in somewhere, right, where something actually crashed, but that they behave differently. I don't remember a single case where that happened. Yeah, I could imagine for more complicated semantics that might be a more relevant thing, but here, at least so far, it didn't really turn out to be an advantage.
Thank you.
All right, one last question.
So you spoke a number of times about keeping things as low level as possible. And one of the questions that I have is, so if you want to have two different languages that are both compiling to Wasm, and then they call into each other, then obviously they need to know, garbage collection is one step towards, okay, now they don't need to know about how they allocate memory, but they do still need to know, how are values represented. If you want to represent objects, if you have two object-oriented languages and then call methods on each other, then there has to be some agreement. Is this something that people have considered? Is there some work towards this end?
So multi-language interop was very consciously not a design goal of WebAssembly, because as far as I'm concerned, that has never worked in practice, right? That's kind of like, there have been projects, like major projects on VMs that claim that that is their goal. In reality, there's always, like even little language impedance mismatches already make the whole thing fall apart. So we very explicitly did make that a non-goal of WebAssembly, which does not keep anybody from, like, if they want their languages to interact, well, what you have to do is you have to agree on an ABI essentially, right? Like you do in native land. And people could do that. They could write a standard ABI and stick to that. That's one part of the answer. The other part of the answer is actually the component model also tries to address that question on a somewhat more higher level. So you have these language, more high-level language neutral interface types that can express data structures in a bit more high level. I didn't show what they look like, but they're very canonical kind of algebraic types if you want. And then multiple languages could speak to each other through those. But that is a relatively high-level model. It does have no shared state whatsoever. So if you need something in between, there's nothing right now that you can just pull out of a shelf and use. But there's also nothing keeping you from defining such a thing.
Thank you.
Great. Well, let's thank Andreas again.